Oh, maybe about 10 seconds. Anybody have an answer? Oh, sure. D? Okay. 4.48. So sigma of T equals, we're given sigma of 0 as 4.2 times exponent of negative T over tau. And we're being asked to solve for relaxation module E sub r. So you mind kind of walking us through what you're thinking? Okay.
5.8 by 4.2, then you get like the decimal 0.190, and then you take the natural log of that, and then you negate it. And then if you take 30 divided by that, you should get this tau value.
How do you like my equation tricky? Yeah. Okay, then what do we get for tau? Sorry, what was that? 18.09. Okay, 18.09. Okay. All right, what's next?
And then you having 10 for each time, and then 18.09 for your tau.
Okay.
Get your
Which, by the way, I don't know if that was actually helpful, but it felt cool to do. Okay, so sigma, yeah, sigma naught,
4.2.
yeah, 4.2.
And that's when you stress, and you divide that stress by your strain of your 5.4.
Okay, and what was the stress right here? Okay, 2.416. And then you said we're gonna divide that by 0.5. And that is what's giving us our 4.48 as the relaxation modulus. Okay, thank you. Okay, there. All right, this one fairly critical, I would say. Okay, we've got a composite of two components. E1, E2 are the moduli. We have volume fractions nu sub 1 and nu sub 2, look like these. The composite modulus must be greater than which of these quantities?
That's why I was late.
Okay, maybe 5-10 seconds. Okay, what do you think? Anyone venture a guess? The okay, why B? We think. Yeah, take a bite. We have
components. One is an upper bound, one is a lower bound. A is the upper bound equation and B is the lower bound equation. Those come from two different assumptions. We assume isostress or isostrain.
And isostress is the
lower bound.
Yeah. Okay.
And so if we're looking at the composite modulus, it'll be somewhere in that range, depending on the compositions, the volumes of the two different matrix or the first space. And so it's going to be greater than the isostress in the lower of the G equations and less than the isostrain equation.
Yeah. Let's just put this one up here for now. So what's our isostrain equation?
It's A.
Yeah, so u sub 1, E1 plus u sub 2, E2. Okay, so that's our upper bound. And then our lower bound, what's our starting equation?
So we're assuming isostress. So we know that each of the stresses, each of the sigmas for the matrix and the disperse space are equal. And once we know that, we can look at the strain. So we were told that the composite strain is equal to the strain of the matrix times the volume of the matrix plus the strain of the disperse space times the volume of the matrix.
And using that, we're gonna get, oh, sorry. This equation here, right? And then solving for E sub CT here, we can get this now.
Yeah, there's two different ways to arrange the equation.
Yeah.
One is one over the top equation, the other is the bottom equation.
Yeah, so with let me go back here. How are we going from this equation to the answer over?
Actually simpler to look at the first equation of those two. We
Yeah.
go back to the other slide.
Yeah.
And we just convert it.
Yeah.
We see that 1 over CT, E sub CT equal to E1 over E1, E2 over E2. So we just convert that and we get.
Sorry.
So yeah, if we take the top of those two equations.
Yeah.
And we just convert it, then we have 1 over CT, CT, which is E sub CT.
Yes.
And then that's equal to the inverse of the right side of the equation. Which is what option B is.
Okay, feel good? So then, and this is called the rule of mixtures, that upper and lower bound. And so if you're given kind of the same problem statement, numerically, if you're given E1, E2, and then the volume fractions, nu sub 1, nu sub 2, you should be able to calculate both the upper bound and the lower bound for these. So that's sort of the learning outcome, if you will. Yeah.
So in our equation sheet, the upper and lower bound equations are denoted by subscripts CL and CT. Do you know what those stand for? Just so I can keep them straight.
Yeah. So CT is transverse, CL is longitudinal. So what's the C? I think the C is just composite, but let me double check that. Yeah, so composite stiffness and longitudinal versus transverse to give a bit of a.
And the transverse direction is going to be the lower bound. Is that what you're saying?
Yes, yeah, transverse is lower bound, and then coming back here, so transverse is that the fibers are aligned transverse, so in this case perpendicular to and then in the longitudinal that aligned the same.
So the transverse is like the weakest.
Yeah. Exactly, yeah. So, yeah, it's like which one do you think would be stronger pulling with the nice stiff fibers in there versus kind of peeling apart the layers there.
Cool, thanks.
Yeah. Okay, next one. This one has to do with the critical fiber length. So, determine the minimum fiber length in millimeters required for an aligned fiber composite to be considered continuous. You're given the fiber tensile strength, D, and the shear strength between the fiber and the matrix. So what's the minimum fiber length here?
Oh, it's actually, okay, so yes. Oh, wait, I need to replace it. So
Anybody have an answer for this one? Yeah, so 21.43. Why C? Anybody want to kind of walk me through this?
Quick question, is that diameter, is that the diameter of the fiber?
Yes.
And does it change? Does it get bigger and smaller, or is it assumed to be constant?
I think we're assuming it to be constant, but it obviously would change if it's.
You'd probably use the smallest one or the large. I guess.
Yeah, I think you'd use you'd end up using the small. This kind of reminiscent of the true stress, true strain a little bit. It's like what's the instantaneous diameter of the fiber?
And then my other question was for the shear stress, I guess that's the strength between the shear strength between fiber and matrix.
Mhm.
But I was also hearing maybe there's something about the shear strength of the composite, and whichever one's smaller, you use that.
Yeah, that is.
Will we ever need to like know which shear strength to use?
I will. I'll double check that during the next one. That's a good question. Yeah, and you're right. There is that nuance of, you use whichever one's lower, but yeah. So on this one, what are we solving for? In terms of the equation here.
Fiber length.
Fiber length. We're given D here, so that's our 10 to the -4th. We're given shear strength, tau sub C, between the fiber and the matrix, 77. And then sigma F star. What's our sigma F star? With, yeah. And is it as simple as this? No, okay. Talk me through it. Oh yeah. Yeah. So with, let me pull up the quick. And yeah, units would be good to. Okay, so we can have aligned, continuous, aligned, discontinuous, or random discontinuous. Going here, just as kind of a reminder of why we're talking about the length at all. If your fiber is too short, it doesn't do a good job of transferring stress between the fiber and the matrix. And so if it's really long, then these regions where it's not doing as good of a job, lessens the impact there. With this critical fiber length, yeah, so the stress transference from the matrix is more efficient with longer fibers. So we talk about fiber efficiency here. There are two equations here. So when L is greater than this critical fiber length, and then we get this relationship for the sigma, or sorry, our longitudinal strength in tension. So these are the two relationships, or sorry, the two equations for the different regimes. Does that? Okay, so for this, (2.2) gigapascal, this one's megapascals. So what do we get for L sub C? The 1 point. Okay. Are we okay?
So for L sub C, we got 1.429,
Yeah.
but then I'm a little confused on where this 15 is coming from. So in your answer slide, you say that the length of the fiber should be greater than 15 times the critical length.
Oh yeah. Okay, give me a second on this one. So this. Yeah, so the 15, whoops, sorry. Sorry, that's for the less than 15 L sub C. Okay, all right, if I come back to that, what you guys are, okay. So, okay. Yeah, 1.429 times 15, basically is what's getting the 21.43.
Right, I'm not quite sure why.
Yeah. And I think it's,
I get that longer fibers will be stronger.
mhm.
I'm just not sure if it's 15.
Gotcha. And I think that it's, that this is what I'll double check, but that, that's how we're defining continuous, more or less. I was just trying to figure out if that was. Okay, yeah, I think it might not be in the slides, but that like the transition between continuous and discontinuous is based on 15 times. It's like 15 times the critical length. I'll double check that though. Give me a second. Okay. Next one. You've been tasked with identifying a material for an ice climbing tool. Identify 3 properties that you consider to be the most important. Explain why. Name 2 other materials characteristics that are not in the list that you consider critical to the performance of an ice climbing tool. And then based on the 5 characteristics you identified, select and justify a material choice. So we'll just start with this one. For this ice climbing tool, what are the most important 3 properties that you would consider?
I would say
Put down here. I would be the point of like it's Saturday's road.
Uh, all right, what are some of the properties and why? Yeah.
Because you have to like hold it, you will it if you're
Yeah, tungsten might not be the right material for lugging up the mountain. Okay, density, yeah. Yeah. You say, yeah, why that one? Yeah, you don't want it to. Yeah, it'd be kind of bad if it shattered. Yeah, and so yeah, anything else gonna come to mind for? Yeah, yield. Well, uh, yield strength would probably be the one a little more relevant there. And like yes, if you had to rank Young's modulus versus yield strength, like you would yeah, any thoughts there on like Young's modulus versus yield strength, why you might want one or the other?
I guess yield strength might be important because you don't want it to like just actually bend while you're up there.
Yeah,
You know, die.
yeah. Yeah, that seems about right. Sorry, it wasn't meant to be a leading question, but yeah, any others come to mind?
With fracture toughness,
Yeah, why fracture
the
toughness?
same idea as ductile brittle transition temperature, but you don't want it to bend or break.
Yeah.
So, and we said that ductile brittle wasn't quite as important as fracture toughness because if it's bending, then you've already failed.
Yeah.
Whether it's bending or breaking.
Mhm.
But if we consider both the yield strength and the fracture toughness, then we've addressed both those problems.
Yeah, yeah. And if you think about like fracture toughness, impact energy, like you're putting this under kind of heavy shock pretty regularly. And then what are these on here? Okay, two other material characteristics that you consider critical to the performance that aren't in this list.
Versions.
Okay. Any others? Hardness? Yeah. Manufacturability, cost, those can come into play as well. So we'll yeah, this is just sort of example there, and then we'll skip that because we don't have a materials table right now. Okay. And next, which of the following would not be considered a primary method to reduce corrosion? Sacrificial anode, part cleaning, coating or plating, passivating material choice. Oh, okay.
Typically, you don't want any like oxidative you don't want.
So what's the answer here? B, okay, yeah, cleaning the part regularly, not a primary method. I also realized I was getting into some review slides. This is not one of the chapters covered in the test. Like technically, there's like a couple problems that they could pull from it, but corrosion is not one of them. Yeah. Yeah, and this was this came a bit as a surprise to me. There are three questions. The last three questions, two of those are material. Sorry, give me a second. It's the materials performance index. So think like safer style there. So two of those are related to that, and then one is a very simple one from the crystallography section that I think you guys will be able to get there. But problems 1 through 22 are the non-cumulative portions, and then because you recently went through the group project group assignments, then I think that should be sufficient for those last two questions there. And then, sorry for the wild card one. I didn't realize there was going to be this kind of wild card question from a previous one. Does that help? I think okay. Cool. Yeah.
So the one wildcard question from like any or just the crystal?
I don't know if it's from the crystallography chapter, and it's nothing terribly complex from there. Okay. So with that in mind, I think it's worth jumping over here. So materials performance index. You want to pick a material for a plate. This is plate B in the image above, or a new canopy. Your biggest concern is the mass of the beam, but it still needs to hold up a load without deflecting too much. Following the Ashby method, you've identified the following. The function is it should support its own weight without yielding. Geometry, the length is fixed, but the cross-sectional area can be varied, and your objective is to minimize the mass of the plate. You'll make these assumptions. The roof load is a line force at the center of the plate. So it's really, it's like a really wide beam. It's supported on two edges, and then the three variables this light material and a cross-sectional area, B times H, of the plate. So first off, sorry, I'm getting the, and then here we have a set of equations and definitions of those. Find the materials performance index is the question here. So let me. So I'll just kind of walk us through this. So mass is going to be density times area times length. And area is this V times H that we were given. The constraint is that it shouldn't yield, so sigma should be less than the yield strength. And then the free variable is the cross-sectional area, which means we can't vary B and H independently. We need to do everything in terms of A, so we'll end up saying H. So we'll do this replacement. We'll say H equals A over B, and then we'll sub that in. Let's see. Second. Maximum, so we're told that the loading is approximated as a supported beam of width B with a point load in the center. Maximum bending stress in the plate is given by this equation. It's sigma equals F HL over 8I. And the area moment of inertia of I equals, I equals BH third over 12. Okay. Since we are at time, I will say, just as part of the study, I'd recommend downloading these slides. The solution to this is in the notes. So if you download the PowerPoint, you open the PowerPoint, and then you look at the notes section, like speaker notes, that is the solution for this one. Again, thank you so much. I really appreciate all your support over the semester, and good luck with the thing. Thanks. Yeah. Thanks.
You're gonna